Okay, so now we proceed with discussing this damage production which is resulting from these. So to recap, in the previous section we showed with MD simulations how in typical dense materials you have a heat spike where you have lots of disorder initially, but then almost all of this disorder recombines. And because of this, if you plot the damage energy production as a function of energy going from low energies below 1 keV like here to keV energies, you notice that the damage production increases on a log-log plot. It looks linear, but however, if you analyze what is actually the slope here, it's sublinear. In here you see the black line is the energy to the power of 0.8, so the damage production is actually sublinear. The reason is that these low energies you don't have heat spike, but then in the end you get to this heat spike regime, you start having a recombination, which then explains why you have a sublinear behavior. Then if you go to extremely high energies, cascades start to split in subcascades, and then you would expect again a linear behavior with damage energy. And here it's important to realize that this is the nuclear deposited energy, so electronic stopping power should of course be counted out, because in metals it doesn't produce damage. And because of this, if you compare the damage production with the Kinshin-Pease or NRT equations, which were introduced in previous sections of this course, you notice that you fall below it, because the Kinshin-Pease NRT predicts energy dependence which is linear with the energy, but what you observe is much less. And this is partly the same data as in the previous plot compared to the NRT level. So in this plot, NRT would be exactly 1. Okay, this line should be straight. So you should have 1, but in reality you observe less than the NRT prediction. This is known as the damage efficiency psi, which is the actual damage observed divided by the NRT prediction. These points are various MD simulations, or in some cases there are also experiments on this. And this is a plot of experiments on iron and nickel and copper. And you see, although the variation in the experiments is very large, you see exactly the same behavior, that the damage production is less than the NRT prediction. But the great thing now is we understand it from the heat spikes. And this RTPA equation, which was mentioned also earlier in this course, describes these recombinations. So what's done is that you put a recombination factor psi, the damage efficiency, which is a function of the damage energy T, and this damage energy one can derive for it the following functional form, where this exponent here describes the sublinear behavior. This is not exactly the same exponent as before, because here you already have T, so this has a different exponent as the 0.8. And then this CRTPA, that's a constant, which means that at very high energies you get a linear behavior. So in these equations, at high energies, this term vanishes, and then you're left with the CRTPA, which is about this saturation level of, as you saw in this plot, roughly this saturation level is here, roughly 0.3, both in the simulations and experiments. So that was now a physical motivation for this RTPA equation of damage production. But now we also discuss another effect, which is experimentally actually sort of easier to measure than the damage production. One also can have practical application. And this is the ion beam mixing or radiation mixing. This means that atoms are replaced or mixed by the damage event. And this, as you can imagine from these plots of heat spike, this can be a quite prominent effect. Now we'll show an animation in initially fully ordered copper 3 gold. This is a good way of plotting it, because you see that the heat spike region, the order vanishes. And if you look at this, that even though you have recrystallization, you can look now that while it's recrystallizing, the atoms in the recrystallized region are not ordered anymore. So you see that you got quite a large region where atoms were mixed, roughly inside this circle now, even though the damage production is much less. And so you see that the cascade actually displaces a huge lot of atoms, even though the actual defect production is quite small. And this NRT prediction disagrees with both quantities. You would imagine that displacements per atom means this number of atoms which are replaced, and originally people maybe thought so, but in fact it's very far from it. So this is some typical data. Many MD simulations have been done which show similar stuff. So if you have this was for copper. So if you, for instance, look at the values already at 2 kV, the number of Frenkel pairs produced is 6. The NRT prediction would be 26, and the actual number of atoms displaced is 370. If you look at 10 kV, you have a factor of 8 difference or factor of 200 difference between the number of Frenkel pairs and the number of displaced atoms. And the NRT value doesn't agree with either one. So these NRT damage productions for metals don't actually agree with any experimentally measurable quantity. And the reason is that this NRT model does not account for the heat spike recombination and atom mixing at all. Well, the ion beam mixing is interesting because it can be experimentally measured, and it measures directly the primary damage state if you don't have any diffusion going on afterwards. And the idea is that to measure it, you form a marker layer, a thin layer of one material inside another, or in the best case an isotope, for instance, iron 58 isotope in regular iron, which is mostly iron 56. And then you irradiate it, and then because of the ion beam mixing, this material in the marker layer will broaden quite significantly. And then you can measure this marker layer broadening, for instance, with Rutherford backscattering or elastic recoil detection analysis or some other ion beam method. And this ion radiation mixing can be considered to be caused by a set of random displacement, a random walk. And this gives an analogy to diffusion, which is a random walk, as a certain guy known as Albert Einstein showed back in 1905. From this ion beam mixing, it has a well-established theory. You can measure the effective diffusion coefficient. So this is diffusion coefficient time. So this is for a certain fluence divided by the radiation fluence and the nuclear energy deposition. You can get what's known as the mixing coefficient. And in practice, you can obtain this by doing this marker layer broadening, looking at the variance of this marker layer before and after irradiation, and this gives this quantity dt. And if you look at this, you get the units of angstrom to the power of 5 divided by electrovolt for this. If you don't believe me, just take the standard units of a diffusion time, fluence, and nuclear deposited energy, and you will find that you indeed get these units. So that was for experiments. Then in simulations, Thomas Diaz de la Rubia and others showed in 1987 that one can obtain the ion beam mixing coefficient, which is at least if we are in a pure random walk regime, exactly the same as the experimental one. Using these equations, you take the initial atom positions and then the atom positions after a simulation and divide by the atomic density and the deposited energy for this diffusion event, and then this gives a mixing coefficient which indeed should correspond to the experimental one. And one can do this and one can compare with experiments. So this here is just to show that this is a range of experiments. You see there is lots of experiments on this, and they are not fully consistent. This Q is not exactly a constant. One reason is that it's not a pure random walk because there is a ballistic component. Other is that diffusion may, after all, in some materials play in, or formation of thermodynamic effects and so on. But anyway, for a given material, they are roughly comparable. But one can simulate then this using a recipe which we developed back in 1998 actually in this reference, and one can get actually very good agreement between the simulated and experimental mixing coefficients. Well, and as I said, they are not fully consistent. But one thing which is interesting is that the experiments are not fully consistent. But one thing which is interesting is that if you look at very similar metals like nickel or copper or platinum or gold, you see that there is consistently a large difference in the experimental mixing coefficients. That the platinum and nickel have much lower mixing coefficients than gold and copper. And the dominant reason for this is simply the melting point. Copper and gold have much lower melting points than nickel and platinum, and this means that the heat spike formed in a collision cascade is larger and cools down slower, and this explains then the difference in the mixing. So in a way you can say that these mixing values are a direct proof as well for heat spikes. And one can also form an NRT-like equation for the ion beam mixing. This is known as the replacement per atom equation. So here this equation is exactly the same as the previous one for the RTPA, except that this psi coefficient is now a different function of the damage energy. And in this case it has a different functional form which increases superlinearly at first, but then saturates towards a linear value in here. See that if the energy here T is much larger than B, then this becomes about 1, so then this becomes a linear function of the damage energy T here. But the reason again to this superlinear behavior is that for the ion beam mixing you have a much more mixing at the when you start getting into the heat spike regime. So at low energies you don't have heat spike, at high energies you do. And that's why there is a superlinear increase. Whereas notice for the damage it was the opposite. In the heat spike you have lots of recombination, so that's why for damage production there is a sublinear increase. And this functional 4, as you can tell, gives very good agreement with MD data, and one can actually also use it to compare with the experiments. And just for reference, here is some values for this constants in the RTPA and RPA equations for a few common metals: iron, copper, nickel, palladium, platinum, and tungsten. These are based on MD data and they are not 100% reliable, but for instance in iron one can compare different potentials and all potentials give values which are more or less the same. They are not exactly the same, but they're in the same ballpark as these B and C constants, and similarly for the RPA B and C. And finally, I'll sort of summarize this discussion of these damage production models first schematically. So this is the NRT deviation, this equation which was saying that you create vacancies and interstitials. Then the RTPA describes the actual damage production counting in heat spike recombination, and RPA illustrates the actual number of atom replacements like in this graph here. And this can be also done, that was a schematic obviously. Here one is a snapshot of an MD simulation where you are plotting potential energy color shows the damage production nicely also after the cascade. This is again a cross section, and then if we plot the atom movement distance, how far the atom moved from its initial position, then you quite naturally see the atom replacements, the mixing. And here is a video now of the same thing, so same event actually. So this is 10 kV self-recoil in iron. So on the left we have the kinetic energy, in the middle we have the potential energy, and in the right we have the atom displacements. So now if you compare the potential energy and the atom displacement, you see that indeed in this particular cross section there is very few defects are visible, just a few atoms here, whereas the number of mixed atoms was quite large, 2 large regions of atoms which have been displaced permanently far away here. On the kinetic energy scale, of course, everything turns blue again when your system cools down. And I'll just run this once more because this is sort of a crucial animation to understand damage production in metals. And then I'll conclude this video. And then next session we will discuss then surface effects. But thank you for this.